Jurassic Park sold you a 6-foot turkey as a nightmare. The real Velociraptor stood waist-high to an adult human, weighed less than a golden retriever, and was covered head to tail in feathers. But the hunting strategy that made it famous, that was very real. And it was the model Hollywood stole, then supersized into a monster. 75 million years ago, in the deserts of Mongolia, this animal wasn't slashing prey open with its claw. It was pinning victims to the ground the way a hawk does, using that sickle-shaped weapon to pierce, not to slice. The most famous fossil ever found preserves one locked in combat with its prey, frozen mid-kill for eternity. What was it really like to hunt alongside this animal at dawn? You might be picturing the scaly, man-sized monster from the movies. Forget that entirely. The real Velociraptor mongoliensis lived 75 million years ago in what is now the Gobi Desert of Mongolia and northern China. It stood just 2 feet tall at the hip, stretched 6 feet from snout to tail tip, and weighed about 30 pounds. That is smaller than a Labrador. In 2007, paleontologists found quill knobs on a forearm fossil, bone structures that exist only in birds and feathered dinosaurs. Velociraptor was not a lizard. It was a bird-like predator with rust and cream plumage, a long stiff tail for balance, and a brain-to-body ratio, suggesting it was smarter than most dinosaurs. But the real question that haunts paleontology is not about size or feathers. It is about behavior. Did these animals hunt alone like modern hawks, stalking small prey through scrubland? Or did they coordinate in packs like wolves, communicating with low calls and tail signals? The answer is locked in the rocks of the Jadokta Formation. In one of the most extraordinary fossils ever discovered, a velociraptor and a protoceratops frozen mid-fight, the raptor's sickle claw embedded in the herbivore's throat. That fossil is the starting gun for our journey. Because once you understand how a turkey-sized dinosaur brought down prey 3 times its size using a piercing claw, not a slashing blade, and then fed its chicks warm-blooded in a nest, you will never look at Jurassic Park the same way again. And the story begins not in a museum, but in the pre-dawn darkness of Cretaceous Asia, as 3 raptors stir in the scrubland and begin their 5-kilometer patrol. The air is cool and dry, carrying the scent of parched earth and the memory of a rain that never came. You are one of 3 shapes moving low through the scrub, your feathered body blending into the gray-green brush so perfectly that a distant observer might mistake you for a patch of shadow. The sun is still an hour from breaking the horizon, but your world is already alive. Insects chirp their last warnings. A small lizard skitters into a crack. Somewhere in the distance, a Tarbosaurus lets out a low rumble that vibrates through the ground and into your bones. That is the sound of something 30 feet long and 6 tons heavy, and it is the reason you never stop scanning. This is the Jadokta Formation, 75 million years ago, a landscape of sand dunes, dry riverbeds, and scattered oases that will one day become the Gobi Desert. But you do not know that. What you know is hunger. You know the borders of your 5-kilometer territory, as well as you know the rust and cream, barring on your own wings. And you know that by the time the sun sets tonight, you will either eat or be eaten. Your body is a contradiction that Hollywood still refuses to accept. You weigh less than a large turkey. Your hip stands at just 2 feet. Your total length, from tooth to tail, tip no more than 6 feet. And every inch of you that is not beak or claw is covered in feathers. Not the shaggy, half-hearted fuzz of some dinosaurs, but true, complex plumage with barbs and veins. In 2007, scientists studying your fossilized forearm found bumps called quill knobs. Modern birds have them. Eagles have them. You have them. That discovery proved once and for all that you are not a reptile in the old sense. You are a bird of prey, engineered by evolution for the scrubland ambush. But here is the thing that changes everything. The feathers are not just for show. They trap your body heat. They make you warm-blooded. Your metabolism runs hot, demanding a constant supply of calories. Every day you fail to hunt, your body begins to consume itself. This is the pressure that sharpens your senses. Your eyes set forward in your skull give you binocular vision that calculates distance with lethal precision. Your nostrils pick up the scent of a carcass half a kilometer away. And your brain, a knot of neurons larger relative to your body than almost any other dinosaur, processes all of it in real time, making decisions faster than your prey can blink. You are not alone. Flanking you are two others. The larger one, a female, walks point. Her tail, stiffened by rods of bone, sweeps behind her like a counterweight, perfectly balanced. The younger male lags to the right, his head bobbing as he tastes the air. None of you make a sound with your mouths. Instead, the female flicks her tail to the left in a signal that means change course, and the two of you comply instantly. This silent language, conveyed through posture and feather position, is the closest thing to a tactical radio that the Cretaceous has ever produced. The question that has split paleontology for decades is this: are you a pack, or are you just three individuals who happen to be walking in the same direction? The answer is not as simple as Jurassic Park would have you believe, and it changes everything about how you hunt. Every few minutes, another signal passes. A raised wing tip means danger overhead. A low crouch means prey nearby. You have seen this before. You have been hunting together for weeks, maybe months. But does that make you a pack? Modern wolves coordinate their movements, assigned roles, and share kills with a social structure that includes dominant pairs and subordinate helpers. Some scientists argue that dromaeosaurs, your family, did the same. They point to trackways in China that show multiple Deinonychus, a larger cousin of yours, walking parallel. They point to the fact that your brain is large enough for complex social behavior. But trackways only prove that individuals moved in the same direction. They do not prove cooperation. And in your entire species, not a single fossil has been found with multiple individuals buried together around a single kill. So here is the tension, the central mystery that drives everything you're about to witness. Are you coordinating a hunt right now, making decisions together for a shared benefit? Or are you simply tolerating each other's presence because there is safety in numbers? And when the attack comes, it will be every raptor for itself? The answer will become horrifyingly clear in the next few hours. The terrain shifts. You leave the open scrub and enter a shallow gully carved by a long-dead stream. The sand is damp here, holding tracks. Your three-toed footprints, each the size of a human hand, press into the sediment alongside beetle trails and the delicate impressions of fern fronds. You are leaving a record. In 75 million years, paleontologists will pour latex into these very impressions and lift them from the ground. Studying your stride length to calculate your speed, they will conclude you could run over 20 miles per hour in short bursts, and possibly up to 40. But right now, you are not running. You are stalking, head low, sickle claw retracted, every muscle coiled. Let us pause for a moment and look at that claw. It is the weapon that made you famous, and it is almost nothing like the movies imagined. Each of your feet carries a single, oversized talon on the second toe. When you walk, it is held up and back, kept razor-sharp by never touching the ground. The claw is about 2.5 inches long, curved like a fishhook, and its cutting edge is not a blade. Under a microscope, it is surprisingly dull. A study by paleontologist Kenneth Carpenter examined the claw and realized it could not slash through thick hide the way a butcher knife cuts meat. Instead, it is a piercing tool, designed to punch through flesh and then grip. Exactly like the talons of a modern hawk or eagle. The hunting model is called raptor prey restraint. You leap onto your victim, pin it beneath your body weight, and drive that claw deep into the throat or belly, holding it in place while your jaws do the work. You are not a slasher. You are a clasper, a pinner, a dinosaurian falcon built to immobilize, not to disembowel. Hollywood inverted the entire biomechanics of your existence. The female stops. Her feathers flatten against her body, and her tail becomes motionless. This is the signal for prey. You freeze, one foot still raised, and follow her gaze. Ahead, at the edge of the gully where the sand gives way to a cluster of cycads, a small Protoceratops juvenile has wandered away from its herd. It is the size of a pig, beak scraping at a low-growing fern, oblivious. This is the moment where the pack debate becomes real. If you are a coordinated pack, the female will position herself downwind while the younger male flushes the prey toward her. If you are not, one of you will simply launch an individual attack and hope the others do not interfere. What happens next will be preserved in the fossil record because a Protoceratops and a Velociraptor, locked in combat, is about to become the most important dinosaur fossil ever discovered. But that is not this Protoceratops. Not yet. Today, you are hunting, and the next few minutes will reveal something about your world that no museum display has ever fully captured. The female gives a single low chirp, barely audible. The young male responds by angling his body away, circling wide to the right. You hold your position. This looks coordinated. But is it? On another day, you have seen the same female abandon a hunt the moment she realized the larger male was not backing her up. You have seen individuals steal from each other, snarling over scraps while the real prey escaped. Cooperation among predators is not a switch, it is a spectrum. Even modern lions, held up as the epitome of social hunting, succeed more often through ambush than teamwork, and they frequently lose kills to hyenas. In your world, the ultimate predator is not another raptor. It is Tarbosaurus. You hear it again, a low thrumming vibration that travels up through the sand and into your hollow bones. The male Tarbosaurus is closer now, maybe 2 kilometers northeast, and it is hungry. A Tarbosaurus does not need to ambush. It simply walks up to anything smaller than itself, opens jaws the length of a rowboat, and crushes the life out of it. But even Tarbosaurus is an opportunist. It will happily steal a raptor kill if it can, and it has learned to follow the sound of distressed prey. This is the pressure that shapes your entire existence. Every hunt must be fast. Every kill must be quiet. And if you cannot finish it in under 2 minutes, you abandon it and vanish into the scrub. The penalty for lingering is death. The young male has reached his position. The Protoceratops juvenile is still feeding, its parrot-like beak stripping needles from a cycad. The female cocks her head, calculating distance, wind, and angle. Then she moves. It is not a charge. It is a sprint so fast the human eye would struggle to track it. 20 miles an hour, then 30. Her feathered body staying low, wings half extended for balance and steering. She covers 50 meters in less than 4 seconds. The Protoceratops reacts late, its head snapping up. But by then, she is already airborne. Her leap is not graceful. It is violent and precise. She hits the juvenile broadside, her feet slamming into its flank. The sickle claw, deployed at the last instant, punches through the skin behind the ribcage, hooking into muscle. She does not slash. She grips. The Protoceratops squeals and tries to buck, but her body weight pins its hindquarters, and her claw holds it like a fishhook holds a jaw. Her jaws close on the back of the neck, serrated teeth sinking through feather and hide. The struggle lasts 15 seconds. Then it is over. The young male arrives a moment later, feathers puffed in agitation, and circles the carcass. He does not challenge her. He waits, head low, making a soft clicking sound in his throat. This is the post-kill etiquette, and it is the strongest argument for social behavior that exists in your world. In a purely selfish system, he would try to steal. But he does not, he defers. The female eats first, tearing into the soft belly, and only after she has swallowed several mouthfuls does she step back and allow him access. Did they coordinate the hunt? The evidence is ambiguous, but they are sharing the kill, and that suggests a bond stronger than convenience. This is how you hunt, not with the cinematic roar of a movie monster, but with silence, speed, and a claw used as a clamp. The strategy works roughly 30% of the time. That number comes from analysis of modern predators. Lions succeed about 25% of the time. Wolves about 20%. A 30% success rate puts you in elite company, among the most effective hunters on the planet. But a 30% success rate also means that 7 out of 10 hunts end in failure. And failure in the Cretaceous carries a calorie debt that must be paid. You cannot afford to miss often. The sun is fully up now, painting the sandstone cliffs in shades of pink and orange. The heat rises quickly, and with it, the smell of the carcass. That smell will travel. In an hour, it will reach the Tarbosaurus. You must eat quickly and then move. The three of you tear at the Protoceratops in a rhythm born of practice. Gulping flesh and bone, your metabolism already converting it into fuel for the next patrol. In the back of your mind, a pair of chicks waits in a nest 3 kilometers away, hidden in a thicket of ferns. They are covered in downy fluff, and they have not eaten in 2 days. Everything you do today, you do for them. And this is where the science takes an even stranger turn. Because until very recently, nobody knew you had chicks. Nobody knew you had a nest. The discovery that changed everything arrived not from a fossil, but from chemistry. Feathers preserve chemical signatures. In the last decade, paleontologists like Jasmina Wieman and Jingmai O'Connor have pioneered a technique that analyzes the molecular composition of fossilized feathers and eggshells. They found evidence that your body ran hot, like a modern bird's. The eggshells show a temperature consistent with an animal that incubated its clutch, not one that simply buried eggs and walked away. And the growth rings in your bones record a seasonal rhythm, a pattern of stress lines that matches what we see in animals that molt and breed on an annual cycle. You were warm-blooded. You brooded your eggs. You cared for your hatchlings. You were, in every biological sense that matters, more bird than lizard. But here is the dark twist. The fossil record has also preserved something else. The moment everything went wrong. Not for you specifically, but for your species. Because the Protoceratops you just killed was a juvenile. And somewhere nearby, its herd is waiting. Somewhere nearby, a much larger Protoceratops, an adult, weighing 400 pounds, with a defensive frill and a beak that can snap bone, has smelled the blood of its young, and it is coming. The female senses it first. Her head snaps up, blood drying on her snout, and she emits a sharp alarm call. The young male looks up too, then you, and through the shimmer of heat rising off the sand, you see them. 3 adult Protoceratops have crested the gully ridge. They are not fleeing. They are advancing, shoulders low, heads swinging, eyes fixed on the carcass of their young, and behind them, almost as if summoned by the scent of confrontation, the deep rumble of the Tarbosaurus rolls across the plain once more. The hunter is about to become the hunted, and the choices made in the next 60 seconds will determine not just who lives and who dies, but what story is written in stone for the next 75 million years. The female does not run, not yet. She stands over the carcass of the juvenile Protoceratops, her blood-slicked snout pointing directly at the advancing adults, and she makes a sound you have never heard her make before. It is not the low chirp of coordination or the sharp bark of alarm. It is a long, rising hiss that crackles with static, the kind of sound a modern goose makes just before it attacks. It is a threat display, and it is meant to buy time. The juvenile's body is half-eaten. The scent of its blood is a beacon. To abandon it now is to lose every calorie you just risked your life to acquire. But to stay is to face 3 adult Protoceratops, each one 400 pounds of enraged muscle, horned beak, and defensive frill. The math is simple. You are 30 pounds. They are a cumulative 1,200. The female is brave, but she is not suicidal. The young male reacts first. He grabs a final mouthful of meat, tears it free with a wet rip, and bolts east toward the gully wall. His claws gouge the sand. His tail whips behind him for balance as he scrambles up the bank and disappears into a cluster of horsetails. The female glances at you, then at the approaching herd, and you see the calculation happening behind her amber eyes. She is deciding whether the meal is worth a fight. The lead Protoceratops makes the decision for her. It charges. A charging Protoceratops is not fast in the way a raptor is fast, but it does not need to be. It masses 400 pounds. It runs with its head low and its beak forward like a battering ram, and the ground trembles under its weight. The female launches herself sideways a half-second before impact, and the Protoceratops crashes through the spot where she was standing, its beak snapping air. The other 2 adults are flanking now, spreading out to cut off escape. They have done this before. Protoceratops herds are not mindless herbivores. They are territorial, aggressive, and fiercely protective of their young. Fossil beds across the Gobi preserve their skeletons in groups, adults arranged around juveniles in defensive formations. This is learned behavior. This is Cretaceous warfare. You run. There is no more calculation, no more weighing of options. Your hind legs drive you forward with explosive power. Your body low, your wings half extended to steer. You hit 20 miles per hour in under 2 seconds. The sand sprays behind your feet. The gully wall looms ahead, steep but not vertical, and you climb it using your sickle claw as a grappling hook, the curved talon biting into the sandstone and pulling you upward. At the top you pause just long enough to look back. The female is still on the ground, dodging a second Protoceratops, her tail thrashing. She is not going to make it up the wall, but she does not need to. She feints left, draws the attacker's head into a lunge, and then cuts right with a burst of speed that carries her into a narrow crevice between 2 sandstone blocks. The Protoceratops cannot follow. Its frill is too wide. It rams the rock once, twice, then shrieks in frustration and turns back to guard the carcass. Silence returns, but only for a breath. The 3 Protoceratops take up positions around the dead juvenile, their flanks heaving, their beaks clacking. They will not leave. They will stand vigil over the body until nightfall, and nothing short of a Tarbosaurus will move them. You have lost the kill. The female has escaped. The young male is somewhere in the brush, and the Tarbosaurus, whose rumble you felt earlier, has gone quiet. That is the worst sign of all. A silent Tarbosaurus is a hunting Tarbosaurus. Let us pull back now from this single day, this single patrol, and consider what we have just witnessed. A 30-pound feathered predator, armed with a piercing claw and a brain built for rapid decision-making, successfully ambushed prey 3 times its size, killed it in seconds, and then lost the meal to a larger force it could not fight. That is not failure. That is life in the Cretaceous. The success rate of a modern lion is 1 in 4. The success rate of a modern wolf is 1 in 5. A 30% hunting success rate, which is the estimate paleontologists have calculated for dromaeosaurs based on their anatomy and the behavior of modern ecological analogs, means that you win 1 in 3 encounters. The other 2, you walk away hungry, but you walk away alive. And that is the only metric that matters in evolutionary time. This is the reality that the first paleontologists to study your fossils completely missed. When Henry Fairfield Osborn described the first Velociraptor mongoliensis skull in 1924, he named it for speed, calling it the Swift Thief, but he imagined it as a scaly, sprawling reptile, a miniature dragon. He had no concept of its feathers, its warm-blooded metabolism, or its nesting behavior. He certainly had no concept of its hunting strategy. That understanding would take almost a century to develop, and it would arrive in pieces, each one more surprising than the last. The first piece came in 1971, and it would change paleontology forever. On a summer day, in the Jadochta Formation, a joint Polish-Mongolian expedition was prospecting for fossils in a sandstone outcrop when someone's rock hammer struck something that was not rock. It was bone, not a single bone, but a tangle of them, and as the team uncovered the block, they realized they were witnessing something no human had ever seen before. 2 dinosaurs locked together, frozen in the moment of their mutual death. A Velociraptor and a Protoceratops, face to face, the raptor's sickle claw buried in the herbivore's throat. The Protoceratops biting down on the raptor's right arm with enough force to snap bone. They had been fighting when a sand dune collapsed on them, or a flash flood buried them alive, and they had stayed that way for 75 million years. The specimen has a name now. It is called the Fighting Dinosaurs, and it is housed in the Mongolian Natural History Museum in Ulaanbaatar, where it is considered a national treasure. You can walk around it today and see the claw still embedded in the neck. You can see the bite marks on the arm. You can see the exact posture of struggle preserved in 3 dimensions. It is the most direct evidence of predatory dinosaur behavior ever discovered. And here is what it tells us. The velociraptor in that fossil was not using its claw to slash. It was using it to pierce. The claw is driven precisely into the cervical region of the Protoceratops, right where the carotid artery and jugular vein would have run. This is a kill shot, not a random wound. The raptor was targeting the throat, exactly the way a modern big cat targets the throat of its prey. But the Protoceratops was not dying quietly. It had clamped its beak onto the raptor's forearm with enough pressure that the bone broke in multiple places. This, too, tells a story. The Protoceratops was fighting back, and if the dune had not collapsed and buried them both, the raptor might have bled out from that arm wound, even as its claw killed the Protoceratops. A mutual kill, a Cretaceous draw. Dr. David Button of the Natural History Museum in London describes this specimen as a snapshot of dinosaur behavior, something we very rarely have. And indeed, the fighting dinosaur's fossil does something that no other fossil can do. It shows us a moment, not a skeleton reconstructed from scattered bones, not a trackway that suggests movement, but an instant. The instant when predator and prey were both alive, both fighting, both about to die. And from that instant, we can reconstruct the entire hunting sequence that led up to it. The Protoceratops was an adult. It was not a juvenile. This was not an ambush of a straggler. This was a direct confrontation between a predator and a fully grown herbivore, capable of crushing the raptor's bones in its beak. The raptor had leaped onto the Protoceratops from the side or the front, not the back. The angle of the claw entry shows that it was not a pounce onto the flank, but a face-to-face attack. This means the Velociraptor was not afraid of the Protoceratops. It was not waiting for the perfect moment. It was attacking head-on, possibly in desperation, possibly in confidence. We do not know which, but we do know that the raptor's arm, the one trapped in the Protoceratops's beak, was already broken. That suggests the fight had been going on for some time before the dune collapsed. The raptor had sustained a crippling injury but had still managed to drive its claw into the throat. That is the behavior of an animal that does not give up, that fights through pain, that commits entirely to the kill once it has begun. But let us go deeper into the claw itself. Kenneth Carpenter, a paleontologist who has studied the fighting dinosaur specimen extensively, made a finding that overturned decades of Hollywood imagery. The sickle claw is not sharp on the inner curve. It is dull, like a worn knife. Under a microscope, the cutting edge shows no evidence of the microscopic serrations that would exist on a dedicated, slashing weapon. Instead, the claw is thick at the base and tapers to a point, exactly like the talon of a modern eagle. It is designed to pierce, not to cut. When you see a raptor in a movie raking its claw across the belly of a dinosaur to disembowel it, you are seeing a biomechanical impossibility. The claw would not cut. It would catch on the skin and slide. But if you drive it into the throat and clamp down, the victim cannot pull away without tearing its own flesh wider. It is a trapping mechanism, a gripping tool. And once the claw is in place, the raptor's serrated teeth go to work on the neck or the spine, severing the spinal cord or the major blood vessels. This is the raptor prey restraint model, and it is the scientific consensus today. Now consider how this changes your understanding of the hunt we just witnessed. When the female hit the juvenile Protoceratops, she did not disembowel it. She pierced its flank with her claw to anchor herself, then bit down on the back of its neck. The puncture wound from the claw would have been deep but narrow, designed to hold the prey still while the jaws did the fatal work. The juvenile died from a broken neck or crushed vertebrae, not from blood loss. The entire sequence took 15 seconds. That is the advantage of a piercing claw over slashing teeth or claws. You immobilize instantly. You control the prey. You end the struggle before it can attract attention. But attention was already being paid. And that brings us to the second major predator of your world. The one that makes even a pack of raptors scatter. Tarbosaurus bataar. 35 feet long, 6 tons, jaws built to crush bone. It is the apex predator of Cretaceous Mongolia, the ecological equivalent of Tyrannosaurus rex, to which it is closely related. A Tarbosaurus does not ambush. It does not need to. It simply walks up to whatever it wants to eat and takes it. Its teeth are thick, banana-shaped daggers designed to puncture armor and shatter bone. Its bite force is estimated at 8,000 pounds per square inch, enough to pulverize the skull of a Protoceratops in a single chomp. And it is an active scavenger as much as a hunter. It has learned to follow sounds of distress. It has learned that where raptors hunt, there will be carcasses. And where there are carcasses, there is a free meal. The relationship between Velociraptor and Tarbosaurus is not just predator-prey. It is a form of ecological parasitism. The Tarbosaurus does not need to hunt if it can steal, and the raptors know this. Every kill they make, they must finish quickly and consume even faster. The scent of blood travels on the wind, and the Tarbosaurus can smell it from kilometers away. If it arrives while the raptors are still feeding, the raptors have 3 options: flee, be eaten, or hope the Tarbosaurus is already full and only interested in the carcass. Option 3 rarely works. This pressure has shaped the entire existence of Velociraptor. The fast metabolism that demands constant calories. The silent communication that allows for ambush coordination without vocalizing. The choice of small prey that can be killed quickly and consumed in a few mouthfuls. Even the feathers may play a role here. A raptor pressed flat against the sand, its mottled plumage blending into the scrub, is nearly invisible to an overhead glance from a predator 8 feet tall. Invisibility is defense. Invisibility is survival. But here is the pivot. The truth that reshapes everything we think we know about this animal. The Velociraptor is not the star of its own ecosystem. It is the middleweight. The second-tier predator in a landscape dominated by giants. And this changes the pack hunting debate in a way that has rarely been discussed in popular science. If you are a 30-pound animal living in a world where a 6-ton monster can kill you with one bite and regularly steals your food, your survival strategy does not revolve around coordinated attacks on large prey. It revolves around avoiding the one thing that can kill you and the 50 things that can steal from you. Pack behavior, if it exists, is not about bringing down hadrosaurs. It is about safety in numbers. It is about having more eyes scanning for Tarbosaurus. It is about sharing a kill, not out of social generosity, but out of the cold calculus that a group of 3 can defend a carcass against other raptors better than a single individual can. This is not the wolf pack of Hollywood. This is a defensive alliance among killers who would just as happily eat each other if the opportunity arose. The evidence for true cooperative hunting in Velociraptor is thin. No fossil bed contains multiple Velociraptor individuals associated with a single kill. No trackway shows them moving in a pattern that confirms coordinated roles. The only evidence we have is circumstantial: a brain larger than average for a dinosaur, the presence of feathers that could signal posture, and the behavior of modern birds that sometimes hunt in loose aggregations. But modern birds also do plenty of things that are not cooperation. A group of hawks circling the same thermal is not a pack. A flock of seagulls chasing a fishing boat is not a coordinated hunting party. They are individuals taking advantage of the same resource simultaneously. And the same could easily be true of Velociraptor. Consider the events we just witnessed. The female made the kill alone. The young male did not assist. He arrived after the prey was already dead and waited to be allowed to feed. The coordination, such as it was, consisted of him flanking the prey while she attacked. But that is exactly the pattern you would expect from 2 individuals independently positioning themselves for the best angle, not a pre-planned tactical maneuver. The fact that they fed together without fighting is notable, but it may reflect individual relationships rather than pack structure. Maybe the female and the young male are siblings. Maybe they have shared territory for months and have learned each other's tolerance thresholds. Maybe on a different day with a different carcass, one would have driven the other away. We do not know. And that is the point. We are projecting mammalian social structures onto an animal that is not a mammal. It is a theropod dinosaur, more closely related to a chicken than to a wolf. Its social behavior, whatever it was its own. We should not expect it to look like a lion pride or a wolf pack. It may have looked like something we have no modern analogy for. And this is where the science takes its most fascinating turn. Because the secret to understanding how Velociraptor really lived is not in its bones. It is in its chemistry. Since 2017, a paleontologist named Jasmina Wieman has been doing something that sounds almost impossible: analyzing the molecular composition of dinosaur eggshells and feathers to determine body temperature, metabolic rate, and even reproductive strategy. Her technique relies on the fact that when minerals replace organic tissue during fossilization, they trap microscopic chemical markers that reflect the original biology. By measuring the ratio of certain isotopes and the structure of preserved proteins, Wieman can determine whether an animal was endothermic, meaning it generated its own heat internally, or ectothermic, meaning it relied on external heat sources. The results for Velociraptor and its relatives were unambiguous. These animals were warm-blooded. Their body temperatures were comparable to those of modern birds, and significantly higher than the ambient temperatures of their environment. They were not sunbathing lizards waiting to warm up before hunting. They were metabolic furnaces ready to run at full speed the moment they woke. But the chemistry goes further. It reveals that Velociraptor had a seasonal molt. The feathers we see in fossil impressions are not just a static coat. They show growth patterns that indicate they were shed and replaced on an annual cycle, exactly like the flight feathers of modern birds. A molting raptor would have looked patchy and ragged for a few weeks each year, vulnerable and likely hiding more than usual. This is a detail no movie will ever show you, but it is a reality of the animal's life. It also means that the plumage we reconstruct in museum models is a snapshot of a particular season. In winter, perhaps the colors were different. Perhaps the breeding plumage was brighter. We do not yet have the chemical resolution to determine color, but the fact that we can determine molt at all tells us that these animals lived in cycles, not in a constant state of sameness. And then there are the eggs. A velociraptor egg is about the size of an ostrich egg, elongated and blue-green in color, a trait we know from preserved pigment molecules. The mother laid a clutch of a dozen or more in a nest built from vegetation and dirt, often concealed in a thicket or a crevice. The chemical analysis of the eggshell shows that the parent brooded the eggs. The temperature of incubation was stable and elevated, consistent with a parent sitting on the nest and transferring body heat. This is parental care. This is a commitment of weeks, during which the brooding adult, likely the female, did not leave the nest except briefly to drink. She depended on a mate or a social group to bring her food. The fact that a brooding female could survive for weeks without hunting is itself evidence of some form of provisioning. Somebody was feeding her, and if somebody was feeding her, then the relationship was more than casual tolerance. It was cooperative, at least at the level of reproduction. So we have a paradox. The hunting cooperation may have been loose, the pack structure may have been fluid, but at the nest, something more enduring existed. A pair bond, perhaps, or an extended family group. The fossil evidence for this comes from a related dromaeosaur called Deinonychus, where multiple individuals have been found around Tenontosaurus carcasses, and where tooth marks from Deinonychus are found on the bones of the herbivore, suggesting that multiple predators fed. But even there, the evidence is debated. Some of those Deinonychus may have been attracted to the carcass after the kill was made. Some may have been killed by the struggling Tenontosaurus and their bodies accumulated around the larger skeleton over multiple events. The fossil record is rarely clean. It is a crime scene with most of the evidence removed. Yet we know one thing for certain. Velociraptors cared for their young. The chicks hatched covered in down, their eyes open, able to walk within hours. They stayed in the nest for weeks, growing rapidly on a diet of regurgitated meat brought by the parents. Their growth rings in their bones show a fast, continuous rate of development, reaching adult size in perhaps 2 to 3 years. In a world where most animals die young, a 2-year childhood is a significant investment. It means the parents pour resources into a small number of offspring rather than producing hundreds of eggs and abandoning them. It means the survival of each chick matters, and it means that when danger threatened the nest, the parents would defend it with the same ferocity that a protoceratops defends its own young. This is the hidden world of Velociraptor that the fossil bones only hint at. A world of nests, molting seasons, feeding trips, and constant vigilance against predators that could swallow a whole family in a single bite. And somewhere in that world, 3,000 kilometers from the sand dunes we have been exploring, another branch of the dromaeosaur family was living a different life. Deinonychus antirhopus, larger, heavier, the real animal that inspired Jurassic Park, and the story of how Deinonychus was transformed into the movie monster. How a turkey-sized feathered predator became a 6-foot scaly nightmare is a story about one man, a paleontologist named John Ostrom, who dug up a claw in Montana in 1964 and changed the way the world saw dinosaurs forever. But that story is a detour, because right now you have a more immediate problem. You are still on the ridge above the gully, watching the Protoceratops vigil. The female has emerged from her crevice. The young male has reappeared from the horsetails. and all three of you are now facing the same direction, staring at the horizon to the northeast. The air pressure has changed. The insects have gone silent, and a plume of dust is rising against the pink sky. Tarbosaurus is coming, and it is not coming for the Protoceratops. It is coming because it has been tracking your scent for the past hour, and it has finally made visual contact. It is 35 feet of muscle, tooth, and hunger, and it is moving at a walk that covers ground faster than you can run. The female gives a single, sharp alarm call and launches herself off the ridge, not toward the gully, but away, south, toward the distant cliffs. The young male follows. You are about to leap when you hear something that freezes the blood in your hollow bones. It is not the roar of the Tarbosaurus. It is the sound of a chick crying. The nest, the hidden nest in the fern thicket, is directly between you and the approaching predator, and the Tarbosaurus has just turned toward the sound. You do not think, you move. Your body has already made the calculation before your brain catches up. You launch yourself off the ridge not south toward the cliffs with the others, but northwest, angling directly across the path of the approaching Tarbosaurus. The sand burns under your feet. Your wings, half extended, catch the hot air rising off the plain and give you just enough lift to extend. Each stride, you are running at 30 miles an hour, maybe more, and it still feels like standing still. The Tarbosaurus is 300 meters away and closing at a walk that eats 10 meters. With every stride, its head, a massive block of bone and teeth, swings toward the sound of the chick and locks on. It has identified the source. It is not going to stop. The nest is ahead. You can see the fern thicket, a splash of green against the sandstone, and you can hear, over the pounding of your own heart, the thin, desperate cries of your offspring. 2 chicks, just 2. The female is their mother. The young male is their uncle. You are their father, and they are screaming for you. This is the moment the fossil record cannot preserve. No bone bed captures the terror of a parent running toward a predator 6,000 times. Its weight to defend offspring that have almost no chance of survival. The stones only record the dead. The living, the desperate, the brave, they leave no trace. But we know this happened. We know because of the chemistry, because the eggshells show that someone brooded them, because the growth lines in the bones show that chicks were fed, because every living bird today, from the sparrow to the eagle, will throw itself at a predator to defend its young. And Velociraptor was more bird than crocodile. You reach the thicket. The nest is a bowl of dried ferns and feathers, your own plumage woven into the lining. Inside, your 2 chicks, each no larger than a modern pheasant, huddled together, their downy bodies trembling, their beaks open, crying for regurgitated meat they will not receive. You have no food. You have no weapon that can harm a Tarbosaurus. What you have is instinct, and instinct is a strange and powerful thing. You spread your wings, raise your tail, and step between the nest and the approaching shadow. The Tarbosaurus stops. It has seen you. Its head lowers, its massive eyes, yellow and unblinking, focus on the feathered creature that dares to block its path. You weigh 30 pounds. It weighs 12,000. The math is ludicrous. But the Tarbosaurus is not accustomed to prey that stands its ground. It hesitates, uncertain, processing the anomaly. That hesitation will last perhaps 5 seconds. It is the only gift you will receive from the apex predator of Cretaceous Asia. You hiss. The same long, crackling hiss the female used on the Protoceratops. It is the sound of a modern goose warning off a fox, and it works on the same principle. Surprise, confusion, the suggestion that you are bigger and more dangerous than you appear. The Tarbosaurus blinks. Its head tilts, and then, from behind you, another sound joins yours. The female, she has not fled south after all. She has circled back. She is standing on the other side of the thicket, feathers bristling, tail thrashing, hissing with the fury of a parent who has already lost one meal and will not lose this one. The young male appears a moment later, flanking her, adding his own crackling threat to the chorus. 3 velociraptors, 30 pounds each, 90 pounds total, facing 12,000. And the Tarbosaurus pauses. It is not afraid. It is confused. It has never seen prey behave this way. Its brain, smaller relative to its body than yours, processes conflict in simple terms. Food runs away. Food does not charge. And then you do charge. Not at the Tarbosaurus. You are not insane. You charge diagonally, a feint, a bluff, darting across the predator's field of vision and snapping your jaws. The female mirrors you on the opposite side. The young male holds the center. It is not coordinated, it is chaos. But to the Tarbosaurus, suddenly surrounded by darting, hissing shapes, the world has become unpredictable. Its head swivels, its tail lifts. It takes a step back, not retreat, just adjustment. And in that adjustment, a space opens. The female seizes it. She bolts into the thicket, grabs one chick in her jaws, not to kill but to carry, the delicate downy body held gently between her serrated teeth, and she runs. The young male follows, empty-jawed, guarding her flank. You are alone now. The Tarbosaurus refocuses. The distraction has ended. It sees the nest. It sees the remaining chick. It sees you, and it lunges. The jaws of a Tarbosaurus are 6 feet long and filled with teeth the size of railroad spikes. They close on the fern thicket with a sound like a tree snapping. But you are already gone. You grabbed the second chick in the half-second before the lunge, and you are running harder than you have ever run. Your legs pumping, your wings half lifting your body off the sand, your chick clutched in your mouth, silent now, limp with shock. Behind you, the Tarbosaurus tears the nest apart, swallowing fern, feather, and the scent of your family in one massive gulp. It will not pursue. It has already spent more energy than it wanted to. It will stand over the ruins of the nest, snort its disappointment, and then turn its attention back to the Protoceratops carcass, which the adults have finally abandoned as the sun climbs higher. The day is too hot for extended chases. Even apex predators conserve their calories. You do not stop running until you reach the crevice the female used earlier. She is there. Your mate? Her amber eyes meet yours. Her jaws are empty. She sets down your first chick, alive, unchewed, and bows her head. You place the second beside it. The young male stands guard at the crevice entrance, his head still low, his breath coming in ragged pants. The nest is gone, but the family is alive, for now. This is survival in the Cretaceous. Not victory, not triumph. Just the continuation of life through narrow margins against overwhelming odds for one more day. And this single day, this 12-hour slice of existence we have reconstructed, is not unusual. It is the story of every velociraptor that ever lived, repeated across millions of years, written in bones that would one day be pulled from the sandstone of the Gobi. Now, let us step back from the immediacy of the story and examine the scientific infrastructure that makes this reconstruction possible. Because everything I have just described, the speed, the feather signals, the parental care, the warm-blooded metabolism, was not known even 20 years ago. The revolution in dinosaur paleontology that gave us the real Velociraptor is one of the most dramatic shifts in the history of science, and it happened largely in the public's blind spot while the movies were still showing scaly monsters. The first domino to fall was a discovery made in 1964 in a badland in Montana by a Yale paleontologist named John Ostrom. Ostrom was digging in the Cloverleaf Formation when he uncovered the fossil of a dinosaur unlike any seen before. It was larger than Velociraptor, about the size of a wolf, with long arms, grasping hands, and a sickle claw on each foot. Ostrom named it Deinonychus anthropus, the terrible claw, and as he studied the skeleton, he realized something that would overturn a century of dinosaur science. This animal was not slow. It was not cold-blooded. It was built for speed, for agility, for active predation. Its bones were light, its posture was upright. Its metabolism, Ostrom argued, must have been high. This was the beginning of the dinosaur renaissance, the revolution that reclassified dinosaurs from sluggish lizards to dynamic, warm-blooded, bird-like creatures. And it was Deinonychus, not Velociraptor, that became the template for the Jurassic Park raptors. Michael Crichton, the author of the novel, read Ostrom's work and was captivated. He interviewed Ostrom. He used Deinonychus as the model for his creatures, but he called them Velociraptors because the name sounded more dramatic, and because Gregory S. Paul, an influential paleo artist, had suggested in a 1988 book that Deinonychus should be classified as a species of Velociraptor. That taxonomic suggestion never gained wide acceptance, but Crichton took it and ran. In the novel, and then the film, the Velociraptors are Deinonychus-sized, 6 feet tall, scaly, and terrifyingly intelligent. The real Velociraptor mongoliensis, the turkey-sized feathered animal from Mongolia, was relegated to a footnote. But here is the twist that makes this story so compelling. Ostrom's Deinonychus was itself feathered. Ostrom did not know it at the time. The Cloverleaf Formation preserved bones but no feather impressions. It was not until the late 1990s, when feathered dinosaur fossils began pouring out of Liaoning province in China, that the evidence became overwhelming. Sinosauropteryx, the first non-avian dinosaur found with direct feather impressions, was described in 1996. It was a small theropod, related to Compsognathus, and its body was covered in simple, hair-like filaments. Then came Caudipteryx, Protarchaeopteryx, Bipiaosaurus, Microraptor, all feathered, all theropods, all close relatives of Deinonychus and Velociraptor. The pattern was inescapable. Feathers were not unique to birds. They were ancestral to the entire group of coelurosaurian theropods, which included Tyrannosaurus rex, Velociraptor, and even the mighty Allosaurus. If you were a dromaeosaur, you had feathers. Full stop. The confirmation for Velociraptor specifically arrived in 2007. A team led by Alan Turner and Mark Norell at the American Museum of Natural History re-examined a Velociraptor ulna, a forearm bone, that had been collected in Mongolia in 1998. On it, they found a row of small bumps along the posterior edge. These were quill knobs, the attachment points for large, pennaceous feathers, the same structures you find on the wing bones of living birds. The paper, published in the journal Science, was titled Feather Quill Knobs in the Dinosaur Velociraptor. It was definitive. Velociraptor was not just covered in fuzz. It had complex, modern-style feathers anchored directly into the bone. The movie monster, with its scaly hide and reptilian sheen, was a complete fiction. But wait, it gets worse. Or better, depending on your perspective. The feathers were not just decorative. They were functional in ways that directly fed into the hunting lifestyle we have been exploring. Feathers provide insulation, which is necessary for a warm-blooded animal with a high metabolic rate. In the cool desert mornings of the Cretaceous, a coat of feathers would keep a raptor's body temperature stable, allowing it to hunt before the sun fully rose. When prey was still sluggish, feathers provide display surfaces, the tail fan, which we can infer from the arrangement of quill knobs on the tail vertebrae, could be raised, lowered, and fanned out to signal to other raptors. The arm wings, though Velociraptor could not fly, could be spread to provide stability during high-speed turns. exactly as ostriches use their wings today while running. Feathers even provide camouflage, counter-shaded plumage, dark on top and light underneath, would break up a raptor's silhouette against the dappled light of the scrubland, making it nearly invisible when motionless. Every one of these functions has a modern analog in the behavior of ground-dwelling birds and birds of prey. The feather revolutionized our understanding of Velociraptor not just as an appearance update, but as a complete re-engineering of its ecology and behavior. And then came the chemistry, the truly radical leap that has only occurred in the last decade. Jasmina Weeman, a paleontologist at Yale, has developed a technique called Raman spectroscopy that allows her to analyze the molecular bonds in fossilized soft tissues. When she applies this to dinosaur eggshells, she can detect traces of the original organic compounds that were present during incubation. In 2019, Veeman and her colleagues published a study on the eggs of oviraptorids and troodontids, close relatives of Velociraptor, and found chemical signatures that indicated a body temperature between 35 and 40 degrees Celsius. That is the range of a modern bird. It is warm-blooded. Cold-blooded reptiles cannot maintain that temperature. Their eggs would not develop properly if buried and abandoned. But these eggs were incubated. They were brooded. The parent sat on them, transferring heat for weeks on end. And if a troodontid did this, a velociraptor, which lived in the same environment and shared the same physiology, almost certainly did as well. The implications are staggering. A brooding parent is a vulnerable parent. It cannot hunt. It cannot flee easily. It is tethered to a single location, exposed to predators, dependent on a mate or a social group for food. The existence of brooding behavior implies a level of social cooperation that goes beyond casual tolerance. If a female velociraptor sat on her nest for weeks, her mate must have brought her food. The chicks, once hatched, were not independent. They required feeding, protection, and teaching. This is a life history strategy called K-selection. Few offspring, high investment. It is the opposite of what we once imagined for dinosaurs, which were thought to lay hundreds of eggs and then abandon them like sea turtles. Velociraptor was a parent. It invested deeply in its young, and that changes the emotional texture of every fossil we have ever found. Consider the chicks we just rescued in our narrative. In a cold-blooded world, their survival would not matter to the adults. They would be left to fend for themselves, and the parents would move on without a backward glance. But in a warm-blooded, brooding world, those chicks represent months of investment. The female has already spent weeks sitting on the eggs, slowly starving, her body burning through muscle reserves to keep the embryos warm. The male has spent those weeks hunting, returning to the nest with food, never once giving up. The death of a chick is not just a biological loss. It is a failure of the entire social unit. The emotion we attribute to this, desperation, fear, courage, is not anthropomorphism. It is the logical consequence of a life history strategy built around parental care. Now, what about the molt? If Velociraptor had complex feathers, it must have shed them periodically. Feathers wear out. They get damaged. In modern birds, molt is an energetically expensive process that renders the animal partially flightless and vulnerable for several weeks each year. A molting raptor in the Cretaceous would have looked ragged, its flight feathers asymmetrical, its body patched with down where new pin feathers were emerging. During this time, hunting would have been more difficult. The animal would have hidden more, relied on its social group more, and perhaps shifted its diet to smaller, easier prey. The chemical evidence for seasonal molt patterns in theropods is still emerging, but the logic is inescapable. If you have feathers, you molt, and if you molt, you have a season of vulnerability. This is a level of ecological nuance that no dinosaur documentary has ever captured, but it is the reality of the animal's life. Now let us pivot to the definitive fossil, the fighting dinosaurs. We have mentioned it before, but we have not yet fully excavated its meaning. This specimen, found in 1971, preserves a velociraptor and a protoceratops, locked in mortal combat. The raptor's left foot claw is driven into the throat of the protoceratops, near where the carotid artery would have supplied blood to the brain. The protoceratops's beak is clamped onto the right arm of the raptor, fracturing the radius and ulna. The two skeletons are tangled together, preserved in 3 dimensions by the sudden collapse of a sand dune or the mud of a flash flood. It is a snapshot of violence, frozen in geological time. What does this fossil tell us about hunting? First, it confirms the piercing function of the sickle claw. The claw is not slashing the belly. It is embedded in the neck, directly targeting the blood supply. This is a precision kill shot. The raptor aimed for a vital structure, just as a modern jaguar bites through the skull of its prey or a lion clamps the throat. The claw was a weapon of surgical lethality, not of brute slashing. Second, the fossil shows that Protoceratops was not helpless. It fought back, and it fought effectively. The broken arm of the raptor indicates that the herbivore bit down with enough force to shatter bone. A Protoceratops beak, powered by massive jaw muscles, could snap the limb of a raptor as easily as you might snap a dry branch. This was not a predator-prey interaction in the style of a lion and a gazelle. It was a fight, a struggle between two animals that both had the capacity to kill the other. The raptor risked its life every time it attacked an adult Protoceratops. The juvenile we saw killed earlier was a safer target. An adult was a calculated gamble, and that brings us back to the pack hunting question. If an adult Protoceratops is a dangerous target for a single raptor, then cooperative hunting would make evolutionary sense. 2 or 3 raptors attacking together could subdue an adult with less risk to each individual. The problem is that the fighting dinosaurs fossil shows a one-on-one confrontation. It does not show a pack. It shows a single raptor and a single Protoceratops, both dying together. If there had been other raptors involved, we would expect to find their bones in the same block. We do not. The fossil provides no evidence of cooperative hunting in the moment it was formed, but it does not disprove it either. Absence of evidence is not evidence of absence. The trackways, however, are where the debate gets really interesting. In 1997, a team led by Philip Currie described a set of parallel trackways from the lower Cretaceous of China, made by several dromaeosaurs moving in the same direction. The tracks were evenly spaced, suggesting the animals were walking together, not rushing. The size of the footprints varied slightly, indicating individuals of different ages. This looks like a group moving as a unit. But does a group moving together equal a pack? Not necessarily. Herds of deer move together but do not hunt cooperatively. Schools of fish move together but do not coordinate attacks. The trackways prove that dromaeosaurs was sometimes gregarious. They do not prove that they cooperated in hunting. The strongest evidence for pack hunting comes not from Velociraptor itself, but from its larger North American relative, Deinonychus. At a site in Montana, multiple Deinonychus skeletons have been found associated with a single Tenontosaurus carcass. Tenontosaurus was a large herbivore, over 20 feet long, far larger than a single Deinonychus. The suggestion is that Deinonychus hunted Tenontosaurus cooperatively, bringing down prey several times their size, much like wolves hunting bison. But even this evidence is disputed. Some of the Deinonychus at the site show tooth marks from their own kind. They may have been scavenging each other. The Tenontosaurus may have died of other causes, and the Deinonychus simply converged on the carcass. The scene is not a clear-cut case of cooperative hunting. It is a crime scene with multiple possible interpretations. So, where does the truth lie? Probably somewhere in the messy middle. Velociraptor and its relatives were likely capable of both solitary and social hunting, depending on the circumstances. A large adult Protoceratops might be tackled alone by a desperate or exceptionally skilled raptor, as the fighting dinosaur's fossil suggests. A juvenile might be ambushed by a single raptor with no need for assistance, but in some situations, perhaps when prey was scarce or when a particularly large target presented itself, individuals that normally hunted alone might come together to cooperate. This kind of facultative sociality, optional cooperation, depending on context, is common in the animal kingdom. Coyotes hunt rodents alone, but will form packs to take down deer. Komodo dragons are solitary, but will mob a water buffalo carcass together, their interactions governed by a strict hierarchy of size and aggression. Velociraptor may have been the same, not a wolf, not a hawk, something in between. A dinosaur with its own unique social rules that we are only beginning to understand. But here is the revelation that reframes the entire mystery. Feather chemistry is now opening a new window into the social lives of these animals. A technique pioneered by researchers at the University of Hong Kong and the Chinese Academy of Sciences can analyze trace elements in fossilized feathers to determine what the animal ate in the weeks before it died. If multiple Velociraptor individuals are found in the same location with similar dietary signatures, it suggests they were eating at the same time and perhaps sharing meals. If their signatures differ, they were likely independent feeders. The same technique can detect stress markers in feathers, lines of arrested growth that indicate periods of starvation or illness. A stressed Velociraptor feather might show that the animal went hungry during the molt season, or that a year of drought pushed it to the brink. These are individual stories written in chemistry that no bone can tell. And through this lens, the story of our three raptors, the female, the young male, and the father who just rescued his chick, becomes not a speculation, but a scientifically grounded inference. The female's body, if we could analyze her chemistry, would show elevated stress markers from her time brooding, her body consuming its own muscle to keep the eggs warm. The male's feathers would show a diverse diet, evidence of his constant hunting to provision the family. The young male's growth lines would show the history of a hatchling that survived a lean year, whose parents fed him even when food was scarce. These are not fantasies. They are the logical extrapolation of data from dozens of modern studies on the biology of living birds and the chemistry of fossilized tissues. The connection to modern birds runs even deeper. If you want to understand how a velociraptor moved, you study the Seriema, a long-legged, flightless bird from South America that hunts small vertebrates by pouncing on them and pinning them. With its sharp claws, the Seriema has a sickle claw, though smaller than a velociraptor's, and it uses it exactly as the raptor prey restraint model predicts, to pin and immobilize, not to slash. If you want to understand how a velociraptor communicated, you study the cassowary, a large, flightless bird of the Australian rainforests, with a casque on its head and a deep, rumbling call that can travel through dense vegetation. Cassowaries are solitary, but they communicate over long distances and will kill a human who gets too close with a kick from their dagger-like claws. If you want to understand how a velociraptor raised its young, you study the hornbill, a bird that seals the female inside a nest cavity with mud while she broods the eggs, dependent entirely on the male to deliver food through a narrow slit. The level of commitment, the weeks of vulnerability, the trust between mates. This is the world of the velociraptor, not the cold-blooded egg-laying of a turtle. And yet the movie industry has given us the opposite. The Jurassic Park velociraptor is a scaly, 6-foot-tall, hyper-intelligent pack hunter that opens doors, plans, ambushes, and kills for sport. It is a brilliant monster, but it is a monster, not an animal. The real velociraptor was an animal, and like all animals, it was shaped by the specific pressures of its environment. the constant threat of Tarbosaurus, the seasonal molts, the months of incubation, the yearly cycle of breeding and feeding that required a territory of 5 kilometers to sustain. It did not kill for sport. It killed to live, and it died often. Of every dozen eggs a female laid in her lifetime, perhaps 2 would survive to adulthood. The rest would be taken by predators, by floods, by starvation. The odds were brutal, and the margin of survival razor thin. Every adult velociraptor represented a genetic lottery winner, a survivor of a gauntlet that had already killed most of its siblings. This is the deeper truth that the narrative of our 3 raptors reveals. The female, the young male, and the father are not exceptional. They are representative. Their day, the dawn patrol, the ambush kill, the loss of the meal to Protoceratops, the terror of the Tarbosaurus, the rescue of the chicks, is not a story of heroism. It is a story of normal life in the Cretaceous. It is the life that every velociraptor lived, day after day, year after year, for 10 million years of geological time. And when the last velociraptor died, at the end of the Cretaceous, 66 million years ago, it was not because they were failures. It was because an asteroid struck the Earth and killed everything larger than a cat. The velociraptor did not go extinct because it was outcompeted. It went extinct because the sun went dark for a decade, and the plants died, and the herbivores died, and the predators followed. The ending was not a judgment on their fitness. It was a cosmic accident. But before that accident, they thrived. And the proof of that thriving is in the fossils that fill museum drawers and the chemical traces that shimmer in the detector readouts of modern laboratories. The proof is in the fighting dinosaurs, frozen forever in their death struggle, a testimony to the ferocity of both predator and prey. The proof is in the quill knobs on the ulna, the silent admission that feathers grew where scales were once imagined. The proof is in the eggshells, incubated at body temperature, the earliest days of chicks that would grow into killers. Now the sun is setting on our day. The 3 raptors have found a new hiding place, a shallow cave in the sandstone cliffs where the chicks can rest. The female is grooming the down of the smaller chick, her teeth surprisingly gentle, while the young male keeps watch at the entrance, his eyes fixed on the plain below. The Tarbosaurus has moved on. The Protoceratops herd has retreated to its own night shelter. The air cools quickly, and your metabolism shifts to conservation mode, your body temperature dropping a few degrees to save energy for the morning hunt. In a few hours you will rise again, and the patrol will begin anew. But for this brief moment, under the stars of a Cretaceous sky that no human will ever see, your family is safe. The chicks are warm. The terror is past, and tomorrow you will hunt again. The new dawn does not arrive with a roar. It arrives as a slow seep of gray light across the sandstone cliffs, barely distinguishable from the starfield it replaces. One by one, the insects resume their dialogue. The distant cry of an Ajdarchid pterosaur, a giant winged reptile with a 30-foot wingspan, echoes across the plain, a sound no human ear has ever truly heard. The world is fresh, washed of the previous day's blood, and for a few minutes, the scrubland feels almost peaceful. Then hunger returns, and with it, the mandate. You stir inside the shallow cave. Your mate is already awake, her feathers fluffed against the morning chill. The chicks huddled beneath her like a living blanket. The young male is at the cave mouth again, a silhouette against the pinkening sky, his head swiveling in the ancient rhythm of vigilance. The Tarbosaurus is gone, its footprints, deep as bathtubs, lead away to the north, toward a distant riverbed. The Protoceratops herd has returned to its own territory, the dead juvenile already stripped to bone by scavengers that crept in during the night. The desert has recycled your failure and your terror. It always does. What matters now is what you do next. And what you do next is the same thing you did yesterday, and the day before, and the day before that. You hunt, not because you are a monster, not because you kill for sport, but because your metabolism demands it. Your warm blood, a gift inherited from ancestors who first kindled the internal flame more than 200 million years ago, needs fuel. Your chicks, their bones lengthening within their downy skins, need protein. The nest that was destroyed yesterday was only the latest in a series of nests that will dot your 5-year adult life. You will build another. You will fill it with eggs. You will brood them, and you will feed the hatchlings, and you will defend them against overwhelming odds. The cycle is unbroken. It is the pulse of your existence. This is the real Velociraptor, not the 6-foot scaly supergenius of the movies, but a small, feathered, warm-blooded parent living in constant, grinding pressure from predators larger than itself, prey that fights back, and an environment that gives nothing away for free. And yet, this animal, this turkey-sized survival machine, was one of the most exquisitely adapted predators ever to walk the earth. The evidence for that claim is not in its teeth or its claws. It is in the long, slow record of its success. Velociraptor mongoliensis was not a brief flash in the fossil record. It existed, in one form or another, across the Jadakta and Barun Goyot formations of Mongolia for millions of years. Its fossils are found in sufficient numbers that paleontologists can study population variation, growth stages, and even injuries. And what that record shows is an animal that lived hard, dangerous lives, and frequently survived catastrophic wounds. We have Velociraptor specimens with healed rib fractures, with broken and fused toes, with bite marks on the skull that show the animal survived an attack by something with teeth the size of bananas. One specimen, collected from the famous Bayan Mandahu locality in Inner Mongolia, has a pathological mandible, a jaw that healed crookedly after a break, meaning the animal lived for months or years with a disability that must have made hunting excruciatingly difficult. These are not the fossils of a fragile species. They are the fossils of survivors, and survivors leave their marks on the world. In 2010, a team led by paleontologist David Hone described a remarkable find: a set of protoceratops, bones bearing unmistakable tooth marks from Velociraptor. Not the marks of a kill, but the marks of feeding, scraped into the bone by serrated teeth as the raptor stripped flesh from a carcass it had not necessarily killed itself. The marks were found alongside shed Velociraptor teeth, tiny recurved daggers that snapped off during feeding and became embedded in the herbivore's bones. This is direct evidence of behavior, as direct as the fighting dinosaur's fossil, but of a different kind. Evidence of consumption, of routine hunger deliberately satisfied. The carcass was not a fresh kill. It had been scavenged, the bones already weathered by exposure. Velociraptor, like virtually all modern predators, was an opportunist. It hunted when it could. It scavenged when it had to. And sometimes it fed on a carcass that a Tarbosaurus had already stripped, risking its life for the scraps. The picture that emerges from these scattered, silent testimonies is not of a Hollywood monster, but of an animal exquisitely tuned to its specific world. It was fast, but not cheetah fast, except in short bursts. It was intelligent, but its intelligence was practical. Spatial memory for its 5-kilometer territory, social recognition for its family group, and the split-second tactical calculation required to hit a fleeing protoceratops without getting its own arm broken. It was feathered, but its plumage was not for flight. It was for warmth, for display, for communication, for camouflage. It was a parent, a mate, a chick rearer, investing years of care into a handful of offspring that might or might not survive. And when it died quickly, often in combat, and its bones sank into the sand to become the fossils that we now excavate, each one a little time capsule of Cretaceous life. Now, let us confront the elephant in the room, or rather, the Tarbosaurus in the scrubland. The most pervasive myth about Velociraptor is not its size or its scales. It is its pack behavior. Hollywood sold the world a pack of coordinated killers, communicating with barks and head bob signals, planning ambushes like a squad of commandos. The reality, as we have explored, is far murkier. But murkiness is not mystery. The scientific consensus, as of the most recent studies, is cautiously honest. We simply do not have enough evidence to declare Velociraptor an obligate pack hunter. The trackways show gregarious movement, not coordinated attack. The associated remains of Deinonychus and Tenontosaurus are ambiguous. The brain size permits social complexity but does not require it. And the fighting dinosaurs fossil, the single most famous snapshot of Velociraptor behavior, shows a solo predator fighting a solo prey. If Velociraptor commonly hunted in packs, we would expect to find at least one fossil of multiple raptors around a single kill. We have not found it. Not yet. But here is the crucial nuance. The absence of pack hunting does not make Velociraptor a mindless, asocial automaton. The social behavior it definitely did possess: pair bonding, nest provisioning, cooperative territory defense against predators like Tarbosaurus is equally sophisticated, just expressed differently. A male Velociraptor that spends weeks delivering food to a brooding female is demonstrating a level of cooperation that would be recognizable to any birdwatcher studying hornbills or eagles. A female that risks her own life to charge a Tarbosaurus and buy her chicks a few extra seconds is not acting on cold genetic programming. She is making a decision, in a moment of crisis, that prioritizes the survival of her offspring over her own immediate safety. That is not pack hunting, but it is something just as profound: parental investment. And parental investment, in Velociraptor, is a direct inference from the chemistry of its eggshells and the biology of its living relatives. The technique that revealed this is expanding. Paleontologists are now investigating fossilized melanosomes, the pigment-carrying structures within feathers that can, under an electron microscope, reveal the original color patterns of the animal. In 2012, a team analyzed the feathers of Microraptor and found evidence of iridescent black plumage, a glossy sheen similar to a grackle or a magpie. No such study has yet been completed for Velociraptor, but the quill knobs on its forearm confirm the presence of large, veined feathers, and those feathers almost certainly had color. Based on its environment, a scrubland desert, the most likely palette is countershading, dark on top, pale underneath, breaking up the silhouette against the dappled sand and vegetation. Breeding plumage might have included brighter color patches, rust red or cream, displayed during courtship. The fossilized feather impressions from related species in China show barring and mottling, exactly like the plumage of modern ground birds. The days of uniformly gray dinosaur reconstructions are ending. The real Velociraptor was probably a strikingly patterned animal, its feathers a mosaic of earth tones and signal patches, as functional as they were beautiful. And this brings us to the final, sobering chapter of the Velociraptor story: its extinction. For millions of years, Velociraptor mongoliensis hunted the scrublands of Central Asia. It evolved, adapted, survived droughts and floods, outran Tarbosaurus, outbred Protoceratops. It was a successful design, honed by the relentless winnowing of natural selection. Then, 66 million years ago, a rock 10 kilometers wide slammed into the Gulf of Mexico, and the world ended. The impact released energy equivalent to billions of Hiroshima bombs. It ignited global firestorms, triggered mega tsunamis, and injected so much sulfur and soot into the atmosphere that the sun was dimmed for a decade. Plants died, Herbivores starved. Predators followed. Every dinosaur that could not burrow, swim, or fly to some remnant of food went extinct. The last velociraptor died in a world of falling ash and cold twilight, its warm blood finally cooling, its chicks, if any, beside it, unfed. The asteroid was a lottery ticket no one wanted, and it won. But the genetic legacy of Velociraptor did not vanish. Dromaeosaurs, the family to which Velociraptor belonged, are the closest known relatives to the first birds. Archaeopteryx, the ur-bird of the Jurassic, was itself a feathered theropod that shared many features with dromaeosaurs. Some paleontologists even classify dromaeosaurs as a lineage of birds that secondarily lost flight. Others place them just outside the bird crown group. The distinction is, in a sense, academic. The point is that when you watch a sparrowhawk pin a songbird to the ground with its talons, you are watching the behavioral ghost of Velociraptor. When you hear a raven communicate with complex calls and tail movements, you are hearing an echo of the silent flag signals that the female raptor used on her patrol. When you see a pair of swans defend their nest, charging an intruder with wings spread and hissing, you are witnessing the exact same threat display that the male raptor used against the Tarbosaurus. The survival strategies of Velociraptor did not go extinct. They were inherited, refined, and are on display every day in the living descendants of the dinosaurs. So what does this mean for the central question of our deep dive? What was hunting really like for Velociraptor in Cretaceous Asia? The answer is that it was a life of constant calculation. Every hunt was a wager against starvation, a risk assessment that weighed the calories of a kill against the danger of alerting a Tarbosaurus. The sickle claw was not a slashing horror movie weapon. It was a precision instrument of restraint, used to pin prey while the serrated jaws did the work. The pack, if it existed, was not a tight-knit squadron of killers but a loose, opportunistic association of individuals who shared territory, shared genes, and shared the crushing pressure of apex predators larger than themselves. The success rate was modest, maybe 30%, but the ones that survived were the ones that kept trying, and they passed that persistence down through their incubated eggs and their cared-for chicks. The real Velociraptor was not a monster. It was a survivor, and survival in the Cretaceous, against the odds that the Gobi Desert threw at it every day, was a form of daily heroism that no movie has ever captured. And yet, the movie version persists. Jurassic Park, released in 1993, permanently fused the name Velociraptor with the image of a scaly, 6-foot-tall, pack-hunting saurian genius. That image is a fiction, a synthesis of Deinonychus anatomy and human anxieties, filtered through the masterful practical effects of Stan Winston's studio and the direction of Steven Spielberg. But the irony is that the film's own success generated the scientific curiosity that ultimately dismantled its monsters. The wave of popular interest in dinosaurs that followed Jurassic Park led to increased funding for paleontological expeditions, especially in China, which yielded the feathered dinosaur discoveries of the 1990s and 2000s. The very film that made dinosaurs frighteningly reptilian also funded the science that proved they were definitively avian, and so the real Velociraptor, the knee-high, feathered, warm-blooded parent, now stands in museums beside its cinematic doppelganger, a silent reprimand to our hunger for monsters. This is the final surprise, the detail that often gets lost. The scientific revolution that gave us the real Velociraptor happened not in spite of popular culture, but partly because of it. The feathered raptor you see in a documentary today exists because the scaly raptor you saw in a multiplex 30 years ago made a little kid somewhere decide to become a paleontologist, and that kid grew up to dig in the Gobi and discover quill knobs on a ulna. The story of science is not a straight line from ignorance to knowledge. It is a messy feedback loop of inspiration, imagination, and evidence, and every museum display of a feathered velociraptor carries within it the ghost of the movie monster it replaced. Now, as we stand on the sandstone ridge and watch the sun climb to its Cretaceous zenith, we can draw the threads together. The male raptor has led his family to a new thicket, a safer one, tucked beneath an overhang that will shield the next nest from aerial predators. The female is already collecting dried ferns and her own shed feathers, shaping a bowl with her feet. The chicks, still trembling from the previous day's terror, are beginning to explore, pecking at insects and testing their legs. The young male, his role less defined, has taken up a watchful post on a boulder, his tail fan spread for balance. The Tarbosaurus is a distant plume of dust on the horizon, indifferent. The Protoceratops herd has moved to new feeding grounds. The world, for this brief Cretaceous moment, is in balance. The hunt will begin again soon, but for now, the family endures. And perhaps endurance is the real lesson. We began this journey with a question about hunting strategy, and we found an answer in a piercing claw and a warm-blooded heart. But what we truly found is a way of life, a rhythm of patrol and nest, of kill and loss, of terror and care, that played out millions of times across millions of years in a desert that is now frozen in stone. The Velociraptor was not a monster. It was an animal, a parent, a survivor, and its story is still being written, one fossil, one feather, one chemical signature at a time, by the scientists who refuse to let the movies have the last word. As for us, we have only to close our eyes, imagine the cool Cretaceous dawn, and listen for the hiss of a raptor defending its young against the shadow of a giant, a sound that still echoes in the call of every living bird. The Cretaceous ended 66 million years ago. The last Velociraptor died buried in ash. But the world it left behind is not silent. It hums quietly in the genetic memory of every bird that spreads its wings at dawn, in the sharp talons of a hawk, pinning a rabbit to the forest floor, in the low warning hiss of a goose defending its goslings. The raptor is gone, but raptorness persists. And the deeper we dig into the chemistry of eggshells and the isotopes locked in fossil feathers, the more we realize that the line between dinosaur and bird is not a line at all. It is a gradient. Velociraptor lived on that gradient, closer to the bird end than we once dared to imagine. Consider the implications. If Velociraptor brooded its eggs, that means it experienced something that looks very much like the patience of a sitting hen, the slow hunger of a parent committed to a task it cannot abandon. If it molted seasonally, that means it passed through periods of raggedness and vulnerability, hiding in the scrub while new feathers pushed through its skin. If it signaled with tail fans and wing postures, that means it had a visual language, a vocabulary of movement that expressed alarm, submission, threat, and perhaps even affiliation. These are not the behaviors of a mindless lizard. They are the beginnings of something we might recognize, however distantly, as a social self. And yet, the mystery is not fully solved. The pack hunting question persists not because scientists are indecisive, but because the evidence is genuinely balanced on the edge of interpretation. A trackway of parallel footprints could be a pack, or it could be 4 individuals fleeing the same flood. A brain-to-body ratio larger than some modern birds could enable complex coordination, or it could simply be the neural hardware needed to process binocular depth perception at 30 miles an hour. The absence of multiple raptor skeletons around a single kill could mean they rarely cooperated, or it could mean that the conditions required to preserve such an event simply never occurred. The Gobi Desert does not surrender its secrets easily. But this uncertainty is not a weakness of the science. It is the engine of the science. Every fossil that emerges from the Jadokta sandstone is a new data point. Every chemical analysis of a feather fragment refines the metabolic picture. Every biomechanical study of the sickle claw brings us closer to understanding how the kill happened. Paleontology is a slow, cumulative process, and the Velociraptor we know today, the feathered, warm-blooded parent, is radically different from the Velociraptor we knew even 20 years ago. 20 years from now, we will know more. Perhaps a new fighting dinosaur's fossil will surface, this time with 3 raptors and a single Protoceratops, and the pack debate will lurch decisively in one direction. Perhaps melanosome analysis will reveal the exact color of a Velociraptor's breeding plumage, and we will finally see the animal not as a dull brown predator, but as a vividly patterned creature, its feathers flaring rust and cream in the morning light. The science is not finished. It is barely beginning. And what does this mean for us, the audience, the sleepers and dreamers who have drifted through 75 million years of history to arrive at this moment? It means that the real world is stranger and richer than fiction. Hollywood gave us a scaly monster, and that monster was thrilling, but the truth is better. The truth is a small animal standing its ground against a giant, not because it can win, but because its chicks are behind it and it does not know how to flee. The truth is a claw shaped like a fishhook, wielded with surgical precision, not to rip, but to hold. The truth is a nest of downy chicks fed by parents who have already lost several siblings to predators and are determined not to lose these ones. The truth is a life lived on the edge of starvation and sudden violence, generation after generation, for 10 million years, until an asteroid from space drew a line under the experiment. We are the inheritors of the survivors, not Velociraptor itself, but its cousins, the birds that threaded the needle of extinction by being small, by being feathered, by being warm-blooded, and by being able to fly or hide or scavenge through the nuclear winter that followed. The impact. Every sparrow at your feeder, every pigeon on a city ledge, every raven that croaks from a telephone pole is a living dinosaur. Not a descendant of dinosaurs, but a dinosaur in the same taxonomic sense that a human is a primate. The Velociraptor is not a ghost. It is a relative, and its story is part of our story. In the broad, sprawling sense that all life on Earth shares a common thread and a common memory written in bone. So, tonight, as you settle deeper into your blankets, as the dim lights press gently against your eyelids, let the Cretaceous linger. Picture the 3 shapes moving through the scrub at dawn, their feathers blending into the gray-green brush. Picture the female's tail flicking left to signal the change of course. Picture the sickle claw deploying at the last instant, not to slash, but to pierce. Picture the chicks tucked under a wing of rust and cream, silent now, safe for this moment. The world they lived in is gone, but the echoes of their lives are still audible. If you know how to listen, listen in the hiss of a goose. Listen in the talons of a hawk. Listen in the patience of a parent. This has been a deep dive into what hunting was really like for Velociraptor in Cretaceous Asia, a journey into the science that replaced a movie monster with a feathered survivor, a parent, a nightmare only if you were a small dinosaur in the wrong place at the wrong time. If you enjoyed spending the night with dinosaurs and want to explore more of history's strangest, most unexpected truths, take a moment to like this video and subscribe to the channel. Drop a comment below telling me where you are listening from and what time it is for you. Knowing that someone in London or Lagos or Lima is drifting off to the same story is a strange kind of comfort, and I read every comment. Now, close your eyes, let the Cretaceous fade, and sleep well. The raptors will be waiting when you return.